So in our videos about the party problem, we talked specifically about how Ramsey's applies to 6 vertices graphically. Now we're going to generalize and prove Ramsey's theory numerically for more general situations where Ramsey's would be applied. So what Ramsey's theorem states is, for an integer kl greater than or equal to 2, there exists a least positive integer rkl, that would be the number of vertices, such that every graph on n greater than or equal to r of kl vertices contains either a clique of size k or an independent set of size l. So we are going to be doing this via an induction proof. And before we start, I just want to quickly define some terms that will be important. Clique is also a very important term in Ramsey's theorem. So when you have a clique, it just means how many connected vertices, do you have of the same color? So a clique of 3 would actually be a triangle where everything is of the same color. Let's say you had a clique of 2, that'd just be one edge where they are connected by the same color. So that's just what clique means. So knowing those terms, we will now get into the induction proof of Ramsey's theory. Now that we have gone over the meaning of this proof, any vocabulary terms that might be needed, we'll now go through the base case of the induction proof. So with every induction proof, you will want a base case. It's just to verify for the lowest possible values. So here we're verifying for the lowest values of k and l. Yes, this is correct. So first we want to verify that r k comma 1 is equal to 1, and then we want to do r of 1 comma l is equal to 1, and r of k comma 2 is equal to k. So just remember back in our previous section, this was talking about you can have a clique of k or a clique of 1. So we know a clique of 1 definitely has to equal 1 because it's just one vertice. One clique literally means one vertice. So it's one vertice for one clique. Similarly, a clique of 1 here, it's just switching places, so it will still be one vertice. And lastly, we have r of k comma 2 is equal to k. So this one is just saying, if you have k vertices and 0 blue edges, then you definitely have to have k vertices. So let's say you have k edges of the same color. So let's just say it was 6, just as an example of our vertices. So let's say they were all of them the same color, where you have something like this, and this is a complete graph, so it's connected to every single vertice. And you have that. So this is our complete graph K6. So this has to have, if it has k cliques, it has to have 6 vertices. I mean, if you have 6 cliques, you have to have 6 vertices if they are all of the same color. So let's say you had one edge that was of a different color, which in this case, we know it's one edge because a clique of 2, remember what we talked about in the vocabulary, is just one edge. This is a clique of 2. If you instead had one of these edges, one squiggly edge, this would no longer have k vertices. So this is saying, if you have k vertices and every single edge is of the same color, and there's no edge of the alternate color, then you have to have k vertices. And this has been verified through our graph, so our base cases check out. And with that, we can proceed to the inductive hypothesis. So, our inductive hypothesis for the Ramsey's theorem inductive proof states, assume for some KL greater than 2, both R of K minus 1 L and R of K L minus 1 exists, and they are both finite. Show that this also exists and is finite. So, in order to do this proof, one of the mathematical inequalities, I should say, that we have to prove is that R of K comma L is equal to, and I'm going to write this down here as I don't want to run out of space, and actually not equal to, I said inequality, it has to be less than or equal to R of K minus 1 comma L plus R of K comma L minus 1. So if we are able to prove this statement over here, we will be able to prove that R of KL exists and is finite. So in the following proof, inductive steps, we will be showing that this expression is true. Now we are on to the inductive step of our Ramsey's proof. So, to start, let n be equal to R of K minus 1 L plus R of K L minus 1. So remember previously we set R of K comma L to less than or equal to this expression here. So now we're setting n equal to this. So by the end of our proof, R of KL, I'm going to write it up here, R of K comma L should be less than or equal to n. If it's not that, we have done something wrong. So we let n be equal to this expression over here. So to start our inductive step, I'm going to be listing these things out numerically. So our first step is to draw a graph G with n vertices. Our second step will be to have one of those vertices be labeled V, because we want a V in the vertices of G where one of those specific points will be V. So when you have one of the specific points be V, if you have n vertices and one of them has been taken, you will be left with just n minus 1 vertices. So you have n minus 1 vertices. And now you're probably wondering, what are we doing with these vertices? Well, we're going to be splitting them into two groups. Connected to V, so split into either connected to vertex V to V, or not connected to V. So at this point, I have said to draw a graph. The reason I haven't done that yet is because we have an unknown vertex n. But at this point, I'm going to be giving an example graph just to illustrate what I mean by this notation and what all of this all means. So I'm going to draw a graph to describe what that means visually, but that's not the graph that definitely represents this. So I hope that makes sense. I'm drawing a visual graph just to explain what it means. So let's say we had n is equal to 7. So then we have something like this. Hopefully I can draw a heptagon. So something like that. And we want one of them to be V, so let's choose this one. So that means we're left with 6 vertices. So that is indeed. So that's what we're doing here. That's just what all of this means. And we want V to be in our graph of G. So now we wanted to split the other vertices into connected to V and not connected to V. So I'm going to just make some random connections here. And when I draw a dotted line, that means that they are not connected. So let's say V was like this, and that, and this, just some random not connected ones. And then maybe like that, and then maybe this is connected, and this is not connected, and this is connected. And let's say we had something like this. And then, so, and like that. And I think I've got all of them. I missed one. Yes. So I believe those are all the connections that are present in a heptagon. So what this means is, let's say I labeled this 1, 2, 3, 4, 5, and 6. So now we can go through. Which of these are not connected to V? Well, 1 is not, and 2 is not, which I forgot to draw in, but it's not. And then 3 is, so we're going to leave that. And then 4 is not connected, and 5 is connected, 6 is connected. So if we were to split these to connected, not connected, this would just be 1, 2, 4. And this one up here, connected, would be 3, 5, and 6. So that's just what all of this part of the inductive step means. So I hope that helps to clarify some of the notation, because I know some of the variables can be a little confusing sometimes. So with that, we're going to move on to the next part of our inductive step. In that part, we're going to be exploring cases of this proof, and which 2 cases we need to verify before we can actually prove that this inequality, that this is less than n, before we can verify that that is true. So previously we had talked about how n is equal to r k minus 1, comma l plus r of k l minus 1. And just remember, before we proceed with the proof, quick reminder, k is the number of cliques in one color, l is the number of cliques in the other color. So before we proceed, I just want to make some definitions such that the graphs I draw will be clear coming up. So S1 represents the K cliques, and this will be represented using a solid line. S2 in the graphs, which is representing the L cliques, will be drawn being represented by a squiggly line. So to proceed, we have two sets that we want to define. So let's first define the set K of K. So in this case, we have that we have 2 cases. We have U is in V of G, but not in the set V. And remember, in our previous section, what this means is that U is part of that group that is not connected to V. But we could also have this situation where U is connected to V. And in this situation, this is when we will be drawing with a solid line, because this is S1. So let me just close off that set. So S2, which is our L, that is equal to U in V of G. Pretty similar, just some slight difference in how it is drawn. So this is saying U not connected to V, and then we have U connected to V. And if it was connected to V, we would have a squiggly line. So this is just some notation that will be used in the proof. So at this point, we can proceed to our two cases. So we have case 1, which, before we start, I just want to say, case A and B coming up for the proof, we'll be using n-1. And remember what n-1 is. n-1 is all the vertices that is not V. So these are not in V. You could even think of it like this. They are not in V. But I'm just going to keep it like this because we want to set this equal to R and K and L. Well, up here we have that n is equal to rk minus 1, L plus rk of L minus 1. So that means just by algebra, this has to just be 1 less than that. So we can write n minus 1 is equal to r of k minus 1 comma L plus r of k comma L minus 1 minus 1. The whole thing minus 1. Because this whole thing was just equal to n. So now that gives us our two cases. So we have case A, and we also have case B of our proof. And case A and case B are how we will be splitting up and what the next section will cover. So case A states that S1, which is, remember, our K, has to be greater than or equal to R of K minus 1 comma L. Additionally, and kind of similarly, S2 has to be greater than or equal to R of K comma L minus 1. So why must this be true, you might be wondering? Well, after this, over here, we can apply pigeonhole principle. And pigeonhole principle tells us that this has to be true. So this is true by pigeonhole. So this is what we will be discussing in our next part of the proof. We will be proving case A and case B. Or not proving, we will be explaining why case A and case B helps to prove that R of K comma L not only exists, but it has to be finite as well. So previously we were talking about how case A and case B can be used to show that R of KL not only is finite, but it also exists. So we will be going more into that. So let's look first at case A. So A. How does this show us what we want? Well, using our inductive hypothesis, which, remember, what that stated is assume for some KL greater than 2, both R of K minus 1 L and R of K comma L minus 1 exists and is finite. And we want to use that to show that K comma L exists. So just remember that's what our inductive hypothesis states. And that will appear somewhere up there. Okay. So using our inductive hypothesis, we know that S of 1 contains a solid line clique. That's what we'll call it. Remember how we defined S1 and S2 previously. So a solid line clique of L. Oh, I apologize. L was the squiggly line. Contains a squiggly line clique of L, or it contains a red clique, not red clique, a straight line clique of k minus 1. And then if we were to add v, remember this is operating on the assumption that n minus 1. So it does not include v. So if we were to later add v back in, then we would have a red clique, which I'm calling my solid clique, of k, because that's just, notice, k minus 1 plus 1. Those cancel out, and this is what happens. So now, similarly, we can do the same for b. And b is pretty similar. So again, we are using our inductive hypothesis. So using the inductive hypothesis, S2 contains a straight line clique of k, or a squiggly line clique of L minus 1. And then if we were to just add v back in, well, this will be a squiggly clique of k for similar reasons as the above. So notice the fact that we have this, and this is verified for both cases, whether you have a clique of L or a clique of K, and this one is verified for, case B is verified for whether you have a clique of K or a clique of L. Oh, this one has to be an L. K, nope, it's supposed to be an L. Sorry about that. So since both of these show that regardless of your situation, you're going to have a clique of L or K or L, this shows that both of these are finite, they exist, and more importantly, it shows what we were wanting to prove. And that is, for any integer, KL greater than or equal to 2, there exists at least a positive integer, R of KL, such that every graph on n is greater than R of K, L vertices contains either a clique of size K or an independent set of size L. And we have just shown that. This one has a size of L, this one has a size of K, and this one has a size of K and a size of L. And I hope I'm not overemphasizing that, but this here concludes our proof by induction.